So yeah, you can start.
Yes, yeah. So thank you for the introduction, Hara. But I also have introduction slide because I took the liberty from last time Lauren presented. So I thought I should also introduce myself in a bit broader way. So there is a one slide for this. But before getting into it, yes. So today I'll be presenting a topic on the structural health monitoring. So we have an axial piston pump here. So we are going to see what are the challenges and what could be the future opportunities for monitoring it. And if I'm going too fast, please highlight me. I will slow down a bit. I get to tend to be faster sometimes, when I'm really carried away. So let's get into the presentation. Hopefully it works. Yes. Okay. So let's start with me. So I come from, of course, India. I think you all know. So I come from this place here, a small circle. It's a small town in the southern part of India. It's called Pondicherry. It was a French town when British were occupying India. So we have a close relation to the French or France, basically. And I did all my schooling. I almost like all my until my adulthood. I was there in this small city here actually, and I did my college in bachelor's in a college called Pondicherry Engineering College from the same place. And the first time I moved out of my own home was when I was doing my masters, which was again like it's further south. If you can see, yeah. Let me just also put the laser pointer just in case. Yeah. So here, so and then this was called Alagappa Chettiar College, and where I did my masters in computer aided design actually. And then, yeah, I started my career. So I started working with a company called Whirlpool for the brand KitchenAid. I was working on coffee grinders and coffee makers, but unfortunately, those products are extinct now. So all the ones that we have now here is new models, but all the ones that I was working is not anymore in the market. And then I moved on for with a company called G Energy, where I was working for 2 years in designing layouts and control panels for the wind turbine industry. Actually. And then I moved to Vestas. I was this was my longest duration. I was working with Vestas for like 10 years as a tooling engineer, where I was responsible for manufacturing tools, which used to manufacture the blades actually. So you know that the blades is quite large. The tooling is even larger than that actually, and we need to produce quite some amount of blades from those particular tools. So I was responsible for those tools, starting from blade all the way up to the finishing tool actually. So I had a kind of like 10 years within Vestas, where I was like working around all the things in the different departments for all the 10 years. And then I finally moved on to Danfoss for like 6 years back, where we manufactured this high pressure pumps. I'll come back to what high pressure pump is. And then, like 2 years back or 2.5 years back, I started my PhD with the SDU, the University of Southern Denmark, and I'm here with ETH as an exchange student. And further on the personal side, yes, this is me and my family. So in my kind of cultural attire or like a traditional attire. So this is one of the event where we are having a housewarming function in Denmark. So this is a picture from there. And these little two princes, like they are the daughters. And finally, like when I have some free time, this is where I spend. I used to have free time. This is where I used to spend. And you can also subscribe me in the YouTube channel. I have a YouTube channel with 1,000 subscribers. And if you want to listen to some Indian music, please click onto this. Yeah, I go with the name Vijay Ira as my artist name. So enough of personal promotion. Let's get into the agenda for today. Actually, we have the first few part. The first part will be the introduction part, where I'll be introducing the axial piston pump and then how it works and the typical application of it. Then we'll go with the physics-based failure detection, where we try to use the physics-based approach for detecting the failures. And then we have the ML-based failure detection. We have also tried that in the company. Finally, then we found out like these were not enough. So then we started the research. So we'll also go through the research objective. And then finally, like I'll touch upon some of the topics that I've been working for the past 2 years, and also what will be the future work that I'm planning to do from now on. So let's look into the overview of the APP. Here you can see an exploded view of a typical axial piston pump. And I also have a small scaled down version of this pump here. I used to have an animation here, but then that was copyrighted material, so I couldn't show it here. But we have a pump here, which consists of a series of pistons. There is a small, like these parts here. I don't know if people online can also see the one I'm holding in my hand. So these parts here is called pistons, which is very tiny part compared to the whole structure of the things. These move in the cylinder cavity. So there is a cavity here. This is the cylinder cavity. So the piston moves inside the cylinder cavity, and for each rotation, this pushes a certain amount of volume of fluid outside the pump, and that is why it is called a positive displacement pump. That's why it's called a positive displacement pump, because like for each rotation, each revolution, you just have a fixed amount of volume that is being pushed. And when you put a restriction on the outlet side of it, then you will start to get your own pressure actually. So the pressure generates when you restrict the outlet flow. And in this case, this pump has the capacity being determined by the volume or the size of the housing, which is the size. So this is a small size pump, and then also the piston sizing. Apart from that, we have a part called the swash plate. In this case, we have a fixed swash plate. In the oil hydraulics industries, we have like even complex pumps where it can change the swash plate angle based on the need of the power and the need of the flow. But in this case, we have a fixed swash plate. So this angle of the swash plate determines the capacity of the pump. But we also have, like, even though it's a fixed swash plate, we have in different configurations, like say like 15 degrees, 17 degrees, which will change the capacity of the pump. And for like, yeah, I can rotate here. I don't know if you can see it. When I rotate it, then you can see the piston inside here. It can move from the bottom dead center to the top dead center here. And when it reaches the top dead center, the volume is pushed out. And when it starts to the other way around, it pulls the water inside actually. And for those online, there is a link here. I'll share this presentation maybe later. So there is a very good animation here which shows the working principle of axial piston pump. I think because it's a mixed group, I'm just taking a bit more time to elaborate it actually. So again, as you see here, like we have different systems. So further down the line, we will see, or I'll be explaining some of the systems which I've been working on for the parts. So it's worth noting that like we have this as a port flange. This is called the valve system, a cylinder barrel system. This is called the piston system, end cover, and swash plate and housing. So these are all kind of grouped into based on the components that they have actually. And the typical application of such plants, like this is purely for the water hydraulics. I forgot to mention that point. So the one that we are working in Danfoss in our group is for water hydraulics. As I said, we also have something for oil hydraulics, but the volume or the size is very limited because you only need high pressure rather than the volume. But in our case, we also need both the pressure as well as the volume to compete with the centrifugal pumps, because the typical application is a reverse osmosis, where we convert like the salt water or like dirty water into clean water passing through our membrane. And here you can see a circuit which is consisting of a high pressure pump and energy recovery device. This is also a product which Danfoss makes, but we'll not see more about this. But the idea here is to recover the energy, because when you have RO membrane reject, which is like rejecting at close to the reverse osmotic pressure actually, which is almost 55 bar actually. So this pressure, if you discharge it to the sea, it's going to go waste actually. We have then the energy recovery devices, which takes these energy, converts that energy into again a mechanical one, and then pushes more liquid into it. So we don't have enough high capacity needed on the pump itself. So we also recover a device, so the efficiency is really high in this case. So we call this the high pressure circuit. And one of the key thing is like the efficiency part, because the reverse osmosis plant, the energy cost is the main energy driver, main driver for the energy actually. It's a main driver of the cost is the energy cost actually. And that's why like the higher efficiency is quite critical, and we have a total efficiency of close to 90 to 95%, given if everything is under optimal conditions. We have 90 to 95% compared to a typical centrifugal pump, which ranges from 85 to 90. So even the 5% boost gives a lot of savings to the plant. And then coming back to the condition monitoring part itself. So what we also, I mean, this journey was started like 5 years back when I joined Danfoss. There was a project where we wanted to see like this is not an intelligent structure. So it is a steel. It's kind of a steel mass which just runs and then produces water if needed when it's rotated. So we wanted to see like if we can make it more intelligent or more smart. So how can we do it so that we can detect some of the failures here? So we want to detect wear, cavitation, leakage, and safety things. So we went on to the literature and then we saw like, okay, we can do this with the help of the available sensors such as RMS, accelerometer, flow meter, and pressure transmitters. Okay, nice, sounds good. So then we started our journey with this. And then with these ones, we wanted to detect these failures. I won't be diving deep into it, but these are some of the failures, which is the after effect or which is due to the phenomena that is occurring here. For example, wear causes some of the damages to the physical component here. So then we wanted to go for the physics-based failure detection because our pumps do fail in a very catastrophic way because it is a rotating component and the rotational speed is somewhere ranging from 1200 RPM to 1800 RPM. So when things fail or when there is some failure inside the pump, then it kind of goes away very fast actually. So then you will have a very catastrophic failure, as you can see from some of the pictures. So we wanted to kind of say if we can detect these failure in advance. Again, as I said, it's the physics based now, where we have these sensors that we have, like pressure, temperature, lubrication flow, vibration, and power. And then we just put these sensors upon the pump. We have two vibration sensors in this case, one axial and one radial. And we also have an inlet, outlet, and a housing pressure and a lubrication flow. In this case, we also started with the RPM sensor, but we found that RPM sensor reliability is much lower than the pump itself. So we kind of removed it and we have a kind of indirect way of calculating the RPM from the vibration sensors. So all good. Then we went to the field installation. We just set up the field installation with the nice, a lot of cables, of course, and the gateway which collects it in the cloud. Then we started to see, then we waited. Okay, so before, I think, yeah. So before this happened, we were waiting for like some failure to happen. Though the pump team were not so happy, we had one failure after 3 years, we had one first failure actually. And we were, hey, okay, now it's the time for us. So let's get into it and then see what this brings us actually. And as you can see, this is a very catastrophic failure. You cannot really identify the root cause, what happened or when and how things happened. So we kind of started our investigation for this. And then, the thing here was like the operator heard a loud noise and then he stopped the pump. Otherwise, it would have even got even worse actually. But this pump was stopped when the operator had a very loud noise in the pump while he was walking around. So it was fortunate that he was having a tour around the pump at the time and the pump failed. So yes, so these are some of the signals we acquired from the pump. So this is an axial direction, this is a radial direction, and you can see these white lines correspond to one cycle of the pump, like 1 RPM, you have one cycle of the pump, which is shown by these yellow lines here. And you can see it's pretty much the same, the axial and radial direction, looking at the legacy perspective. And we did some kind of a filtering, like low pass and high pass filtering on the signals. And then we could see like clear peaks for each of the 9 pistons. So of course, this is a piston pump. So the piston frequency is the dominating frequency rather than the running frequency. So we could see like 9 shocks or 9 peaks between each revolution actually. And then we kind of put this in a polar plot where we started 0 as the reference point, and then we chopped each of these signals, put them together on top of each other for the whole revolution. We took a signal of 48 kilohertz and then it runs for 3 seconds. So we divide these whole 3 seconds of data into chunks for each revolution and then put on top of each other, which is shown here in this plot. And again, we do the standard frequency thing like the FFT spectrum, RMS, peak to peak, cortices and things like that, which is the standard according to the ISO vibration standards. We calculate all these features, but then what we found out is of course, the quality of the signals which we acquire is quite high compared to the running frequency of the pump, because the running frequency is close to 30 hertz and we are acquiring at 48 kilohertz. So we have enough resolution in the signal of the frequencies. But the amplitude of the vibration also we can see for each individual pistons when you do the filtering. Without the filtering, you're not able to observe it. But when you do the filtering, you can see the amplitudes of the vibrations. You can also see the shocks of the 9 pistons are very similar in normal operating conditions. When things change, we will see how it affects. But in the normal operating conditions, the shocks are quite similar. But we also see here is like there is some significant unbalance in the pump for this particular pump, because of which we have this amplitude modulation that is happening on the pump at the running frequency. So we also have some unbalance in the pump in this case. And then, yeah, and these unbalance could be due to some of the standard according to the literatures. But then what we did is we then took the failure data of the pump and then we did the same thing. But in this case, we also now here we have the chop plot in this left hand side here. We kind of put it on a linear plot here to see what is really happening. In this case, we can see that this is the first half, one half of the stroke, and this is the second half of the stroke. And in the first half, you can see there is a much a bigger noise compared to the lower half actually. And there are a lot of phenomena that can explain this. But one phenomena is that like when you have high pressure, the leakages are more because of the pressure difference. So it causes more noise on the data compared to the low pressure side where the frequency, so the pressure difference is much less actually. And yeah, here I don't know if you can see it, but here there is a red circle around the noise level actually. I think it's not clear, very clear, but this is kind of the band that we are seeing, like how the band of the noise level varies with respect to the pump over time. So when you do this for like 12 weeks earlier, so you can see like we had the luxury of like 3 years data to analyze. So we started with how early we can detect, and we can see like from 12 weeks earlier, we started putting it almost close to 4 weeks earlier, we can see some changes to the data here. So we were quite happy that, okay, so if we have like 4 weeks of time to detect these failures and then intimate the customer, then they will be happy, they will be able to stop the pump before catastrophic failure and also can investigate the pump further to analyzing the root cause. But yeah, but then of course the reality is like when we took this data and then implemented it in the field, we know that it was not working because each pump was having a different signatures, I would say actually. But yeah, I think this thing I will skip actually, which I explained it in the slide already. So this is just an explanation. If you want to read through it, we can do it. But the key outcome is this can be implemented because we were not able to validate it. How can we reproduce the same results, you know? So we were not able to validate it without knowing the root cause. We couldn't really put this pump and then see if we can run the pump. So we tried to imitate the failure by creating some known failures, like by creating failures in the pistons or creating failures in the other systems, and then see if it was matching the data that we have obtained. But we couldn't validate it. So it was not possible to replicate the failure itself actually. But also what we saw is there are some other failure modes that we have observed in the lab, which was also having a very similar characteristics actually. So then we got really worried. Okay, so this is due to this failure or this failure, or even some of the normal pumps were having higher noise actually because of the tolerance differences within the pump and the manufacturing process. So that was also one of the key challenges, and the threshold levels. So even if you combine this methodology and then come up with the threshold levels, but then this threshold levels will not be applicable for the next pump actually. So these were all some of the challenges for implementing the physics-based failure detection. So then we went to our nice friend machine learning because everybody was so fond of machine learning. And then we had a very good company who were also kind of trying to sell their software to us actually. So then yes, why don't we do the machine learning part? So we did the trial run here. I think we have put that right. So we did the trial run with that. Here you can see that it has again 2 sensors. One is the axial sensor and the radial sensors. And we also did a kind of experiment where we mark each pistons and then it conditions. We also measured each piston to see like if how much is the difference, and we almost matched the pistons in terms of the dimensions so that we can get similar phenomena for all the 9 pistons. And then we changed the operating conditions. In this first part, like we were doing it at a constant run, and then we also did a sweep because our pump does not always run in the constant RPM. Even though like most of the pumps run at 1500 to 1800 RPM, but all the pumps does not run at a constant RPM. It run the RPM ranges from 700 to 1800. So we did a sweep also for that. And then in the second day, we started changing the pistons. We had like shoe failure, loose pistons, stuck pistons, and then we have also some. We also reverted back to the original pistons and original valve actually. Then yes, at the constant RPM, I mean, of course, I don't know what's happening inside. This was kind of a, sorry, this was kind of a black box for us because it was the company who had developed this model. So we just fed the data to this model, and then they kind of came back with these 4 nice divisions where like we can detect the normal and then the loose piston, damage, and the stuck piston. So of course, machine learning, like this is kind of a supervised learning where we taught the model based on the timestamp here, like this data is belonging to original thing, this data is belonging to this actually, and then it was able to easily identify, like when we then ran the pump again, then it was able to detect the right thing actually. But in the case of the sweep, RPM sweep, where it was running from 700 to 1500, here you can see the model was performing below par, where you can see a lot of crosstalks between the different failure modes and the normal modes, and it was not able to detect the same way. So, but what they came up is like if we have more data to train, then we will be able to implement this model, and then we can improve the model detection capabilities. So okay, so the based on this idea, what we did is then we took our own thing and then we started, because we have these already in the field, so we have enough data in the field. So we started putting these things into the machine learning algorithm, and then we started plotting it in our own method actually. And here we can see like this is a normal pump, and then even with the normal pump, you could see like there is 2 clusters that is forming already actually. And we could not explain what is happening here because when we open the pump and then inspect the pump, we could see that everything is fine and pristine. So we don't have any, or at least we couldn't detect physically like any damages or any changes to the pump actually. So then this gave us, okay, so now the confidence even went down. Okay, so now even for a normal pump, if it is clustering, so what will we do? How can we explain it to the customer? So again, like so the machine learning also failed, and then we also found that that the pumps have different characteristics on its own for the physics-based learning also. Sorry, physics-based failure detection also. So what can we do? So this is sorry about this. So what can we do? So this is what the challenge is. So this is what led me to the research basically. So we of course, this is a summary of it. We know that the pump dynamics changes between each start and stop, and each pump is different and has its own fingerprint, which we saw earlier. Also, the failures, number of failures in the field is very limited. We had like 1 or 2 failures in the field so far, and we couldn't do much with the failure data. And most failures are catastrophic, so we are not able to find the root cause for the failure itself, and it was beyond investigation. And also there is a lot of, I mean, yeah, lack of failure, but also lack of literature for the water hydraulics, because for water hydraulics, there are certain phenomena like cavitations is one of the main cause for failure in some of the parts, which is not covered for the, which is not the same for the oil hydraulics actually. So we don't have enough literatures to also work with the water hydraulics part. So that's where like we came up with an idea. So to solve the pump dynamics part, can we use the digital twin like a finite element model, and to study the force variation, quantify these force variations. Again, for the each pump as is different. So can we identify, or can we understand the cause for the variability and then eliminate it by using the finite element model updating, and then eliminate it from the model itself so that the the characteristics from the dynamics is different from the uncertainty actually. And of course, for the failures, we can simulate the failures. If we have an accurate model in the entanglement, then we can simulate the failures. And then we can generate the failure data through the simulation. So simulation, we can run it even without any needs. So we have to only have the computation power to run through the simulation to generate the failure data. And this is what is my research is all about. So we have like divided this task into 7 work packages. Of course, as with any research, the first one is the literature survey. Then we have the financial model, and we wanted to then introduce the uncertainty part in the financial model. And we wanted to do an extensive testing to capture the variabilities and update the model based on the experimental data and the financial models. So currently I'm in this phase now in the module 5. And once this process is done, then we will simulate the module 6 and 7. Module 6 is simulating the failure data, and module 7 is ML-based CM algorithm or CM solution once we have the failure data from the digital twin. And here we propose this hybrid modeling technology because we also have access to the simulation as well as the experimental data. So we do the FE modeling, we do the model analysis, and then we extract the frequency and the mode shapes here. We at the same time we do the experimentation and extract the model parameter using SSI, and then do this FRF based model match the modes using the FRFs, and then see if these two can match. And if they don't match, then of course we have to update the model in here, then do the model analysis, and then until it matches, we do the model updating, and then we have an updated FE model. So yeah, this is same put in other words actually. That was in flowchart, and here like it's in a form where we are trying to capture the assembly dynamics in the stationary components through the FE model, and then the internal components through the data-driven model. And when we assemble them together, then we get the whole APP assembly. So that's the idea at least. And then we call this the digital twin, so that we can generate whatever data we want from these digital twin. So then comes like how can we capture the uncertainty part? And this is what I've been doing for the past 2 years. So we have been working on this. Of course, there is a lot of literature available on this. So we have been doing the impact testing, shaker testing, and then see which one was suiting for us. And then we have extracted the model parameters. And from this, we have studied how much the model parameters vary. And based on this, we also plan to do the model updating. So this is kind of an overview of it. So first part is the experimental part, where we did the, so the pump itself is so complicated actually. So if you want to develop a method for the whole pump, I think it's probably not a 3 years PhD. So it takes probably a lifetime of effort to develop it for the pump. So we started with a simple component, which is the housing here. And we started to quantify what all the uncertainties that it can happen. So one is the manufacturing variability, the other is the material properties, and then the boundary conditions. So in order to do the manufacturing tolerance variations, we did more than one component in the shaker test. We got, we couldn't have a bunch of components, but in order to kind of have at least simple statistics, we did on 2 housing components, and we did on 3 boundary conditions. So one is on the hard foam, the other is on the soft foam, and the third one is hanging in the bungee cords actually. And we did this repetition for 10 times, and each repetition was like repeated 5 times. What I mean by repetition is like between each repetition, we kind of disassemble the whole thing and assemble it back again. But in this condition, we repeated it 5 times. So why we did it is we wanted to capture the measurement chain variations, which is captured by repeating the experiment in the same setup. But then we also wanted to capture the assembly variations, which is like removing and connecting it again. So in this way, like we could simulate both the assembly chain as well as the measurement chain variability. And of course, the boundary conditions will change here. And we did the total of 400 experiments. I will quickly run through this. I don't know how long should we present. Like we should leave some question time, right? Okay, yeah. Because this is also, I have made a paper on this and presented it at the EWSHM last year, this June actually. So here again from the nature of the component itself, we could see like we have very closely paired modes in this case. So there's two modes that is very closely paired. We could clearly see the difference in this case here, but there was also two modes in here, which is not clearly seen. So if you like use a peak detection method, I think we won't be able to detect the two peaks here clearly. And similarly, like here, we have a difference in the change between the support conditions. The red one is the hanging boundary condition, whereas the blue and the green is on the foam. Of course, the stiffness changes between the soft and the hard foam, but we could see they are both matching the eigen frequencies, whereas in case of the hanging, it was shifting a bit. And in this case here, I think, yeah, again, we could see like there are two modes in the foam support, but in the case of the hanging, we could not detect the second mode. It was only detected as one mode here. Okay, I'll zoom here. So this was kind of the observation. Oh. Okay, this was the observation from the things. So then we went on to the SSI to extract the stable modes from these things. And you can see like this one consists of the FRF part and the CMIF part here. And we have the orders versus the frequency here where we are able to detect the stable modes from this. And we also calculated the damping ratio from this. Of course, I will leave a link to the paper if you want more details on these and how these are extracted and things. So we also have a code which we can share. Of course, it's a standard SSI tool. And we also compared the mode shapes from the FEM. And we kind of plotted the first modes. We kind of grouped them into different modes, mode 1 to mode 4 here. And similarly, mode, it's a bit slower. It's a heavy graphic, so it's behaving a bit slower here. Yeah, okay. Yes. So here from mode 5 to mode 7, mode 8 here. And in so here, I think the next slide I'm summarizing the whole thing. Let's see. Yeah. No. Okay, this is hidden. Sorry. Yes. So here is the summary of the outcome from the experiment. So you can see like the boundary condition, the support has maximum impact on the eigen frequencies and also the damping ratio. So this is a plot showing the frequency versus the damping ratio. And in some of the cases, we were not able to excite the modes exactly. For example, in the mode 7, as I said, we were not able to see the modes in the hanging condition that could be due to the lack of excitation. So we couldn't excite this particular mode when it is hanging because of the free motion. But in most of the cases, in all the other cases, we could see that the hanging boundary condition had a lower shift towards the natural frequency compared to the foam-based support. Whereas in case of the mode 8, it was all in the same frequency range, but the damping ratio was kind of changing. So this was key for us to further work on the parental model updating. And here is the reference for the paper, the EWSHM. Why is it slow? A lot of picture here. Okay. And then after this, we will continue with the whole pump. So this is a whole pump setup. We started again collecting a lot of data for other components like the cylinder barrel, the intro, the whole system that I mentioned in the first slide. So we started collecting a lot of data. So we ended up with more than like 1,000 experimental data sets actually. So I have access to these 1,000 experimental data sets. If anybody wants to work on them, you're welcome. But the plan here is to extract the model parameters from these and then use that for updating the fine-tuned model. So this is what I've done so far. And now I'm going to focus for the next 5 minutes quickly on the part I'm doing right now. Of course, we wanted to do the model updating on the finite element. So directly applying it to the pump was a bit of challenge. So we took a simple example of the beam. We did the same experiment on the beam. We did exactly the same steps. Of course, we can solve it analytics also. We can get the mode shapes here in the analytical form. Then we did the same steps like exiting with the shaker and then calculate the FRF and the coherences here. We could see very clean things on three. Okay, I just forgot. Like here in this case, we had three sensors. Yeah, we had three sensors and the excitation was at the 0.0 here. So we had measured the three sensors here, and these are the three outputs from the three sensors. And then we also did the SSI here and extracted the stable modes. So in this case, of course, we don't have the closely paired modes because it is a beam. It's not symmetric. So each modes were clearly identified and was able to clearly run and then it was also faster than the SSA on these ones and easy to identify them. We then went to COMSOL, solving the same problem and then extracted the mode shapes and the mode frequency from there. And we extracted the K and M matrix from the COMSOL. We then took it to the MATLAB and then we started using the penetrant model updating part using the MATLAB. And here you can see like we used only the frequency, eigenfrequency as a parameter for updating the model, but also we use the Mach assurance criteria to match the frequencies. So what happened is like sometimes the frequencies were, when it's closely paired frequencies, the mode shapes will vary a bit. As in the case of the housing, the mode shapes is like when you have a closely paired mode, you have one mode that is on this side, the other mode which is perpendicular. So in this case, the frequency will only vary slightly, but the mode shape, the phase will be out of phase actually. So that's why we wanted to, even though we are using only the eigen frequencies, we wanted to also take the mode shape by taking into consideration the Mach and then see if we want to match the right mode shapes to the right eigen frequencies. And we did that here. You can see like the first three modes are quite clearly matching on the Mach as well as the frequencies here. And this is a mode from the FEM mode shape, and the daughter ones is the experimental mode shapes. And we then use the eigen sensitivity based method for updating the penetrant model. We could achieve a very good result from these actually. I think that is probably the end of this presentation. Of course, the next steps, what we can do with the next steps is we wanted to extract the statistics of the model parameter. So we have the 1,000 experiments. We could easily get like if you solve it for 1,000 times in this FE, I think we get the similar results on the FE part. So we won't be able to capture the variability. So we wanted to come up with the statistics for the model parameter extracted using the experiment and then propagate it to the FEM on the parameters. For example, the Young's modulus or the support stiffness. How much variation on these parameters will give us these variations on the model parameters. Solve all the Fandel models like we are now doing for each individual component. We did the experiment and then solve the FE model and then propagate it according to the sensor positions and then see if we can get the same results. And of course, we will not get the same results. So we wanted to update the pendant model based on this and then assemble the complete model, updated model, and we will get the final pump model. And then, of course, as I said earlier, we will use this model for simulating the failure data, and we have the possibility to validate the same through some experimental data from the lab in Danfoss. And this is, of course, as I said, we will not solve everything that is as a part of the PhD. So we still have a lot of other future opportunities. One thing that is interesting is this virtual sensing technologies, because you can see the pump is really closely packed because of very high efficiency. The tolerances are very close. So there is literally no space inside the pump to put a sensor. So we are using the reciprocity principle. So we are trying to put the sensor here and then see how we can get the characteristics transferred from the force excitation to the sensor itself. But if we can eliminate the effect of the housings, the housing is, in a sense, like if we don't have any leakage, we can take this housing away. Only the cylinder barrel and the piston itself is enough. So housing is only a structural member. So, but it also suppresses some of the dynamics of the pump. So how can we then eliminate the effect of these static components? So that is one way. And then we want to also do some sensor fusion. So we now only consider the vibration data We only use the vibration data as one of the key inputs for the condition monitoring, but can we also use the other data available like pressure and temperature and lubrication flow? And we also want to expand the domain and the physics. For example, right now we are only working under 60 bar RPM. So can we expand it to 120 bar, or can we increase the temperatures, or can we use some other mediums like in some of the industries where mining industries also they use some of the brines and things like that. So can we use in those other applications? And of course, we are only working on the one family of pump or one particular pump I'm working at the moment. So we can also expand it to the family of pumps. And one other interesting feature is this feature enhanced failure detection. This is like a kind of a thing we have been discussing. What that means is like if we can create or engineer some features in the pump which can amplify the effect of the failure. For example, like if a shaft failure happens, like we can put some kind of unbalance in the shaft itself, which will amplify the shaft failure when it comes to it. So similarly, we can think of some other features which can amplify the effect of the failure inside the pump. And of course, the other standard things we can calculate the remaining useful life. And other key thing also is we are not concentrating on the component at this point. We are only focusing on the whole pump as such right now. But can we do a prognosis like which component is failing? Is it the piston? Is it the port plate which is failing? So can we also do that in the future? And yeah, finally, can we use this pump in any other applications? We can also do that from the digital twin and then simulate all the things before we can put this under testing actually. So yes, thanks for the opportunity. I think that brings to the end. I haven't put any questions here, but yes, you are welcome to ask any questions. Thank you.
Thank you, Vijay, for your presentation. So we can open the floor for questions, like both here and online.
Can I ask a question? So I know actually there have been a lot of studies in the field of SHM about rotationary machines, like the motors of a car or airplanes. And have you tried to use validate their method? Because this is also a rotationary machine.
Yeah, this is also a rotational thing, but that's where the challenge is because the characteristics of the pump is determined by the piston characteristics actually. So the piston dominates the vibration signatures actually. So even if there is any other failures or anything else, it gets suppressed by the action of the pistons. And because we are dealing with high pressure, the amplitude of the shocks from the piston itself is too high that the rest of the things get suppressed actually. We have been looking at some of the other applications from the oil hydraulics, but as I said, the oil hydraulics also has a higher damping effect than the water things actually. So we couldn't directly employ any of the methods.
But for example, like the engine of a car has many cylinders.
Yes.
Cylinders is similar to the piston.
Yeah, yes, exactly.
Do you think there's some methods you can use?
I think, yeah, we could use that actually, but I think I haven't explored on many of those. But the ISO standard is also coming from those kind of things, right? So we have ISO standard for the reciprocating engines or reciprocating compressors. And we tried, I mean, the first part that we did was the physics-based thing, which is measuring the vibration signature and calculating all the statistical features actually. So that is purely based on the vibration standards, which is probably from some of the literatures. We couldn't use that directly because our pump were varying from installation to installation. For example, one pump had a hose as the outlet connection, whereas in the other side, it was like a solid pipe. So we couldn't kind of standardize it as a single method. So that's where like we feel like the variability of the operating conditions is huge that we couldn't come up with one single method to or to capture all of the variability.
Yes, thank you.
Yeah.
Any other questions? Also online, somebody has a question, they can unmute themselves. Can I ask a question? It's a bit more conceptual, I would say. So you were showing in the beginning, like the types of damas you can have like in the pumps.
Mm-hmm.
So, are those like types of damas like brittle in the sense, is there like some kind of warning sign? For example, you said you haven't modeled failure still, right?
Yeah.
So how do you imagine like how would you like model failure in this case, like in your model, so that you take into account damage? Because I guess like I don't know if it's too brittle. I don't know. Is there a warning enough, like so that you can, you know, that you will have damage at some point, or is just like okay, there is the sound. I also got like the signal in the accelerometer, but you know the damage is already done. Like you know some kind of warning that you expect to have.
Yeah, I mean, that is the key challenges for us, right? Because as I said, we could not really investigate the root cause of the failure. So we didn't know like if it was a piston that was causing the issue or if it was a coat plate. But we have certain idea from the experiences so far what can cause some changes in the type of operations. So that's where like we can, for example, like this peak material, yeah, this damage. Yeah. So yeah, in this case, we have this is the peak material actually. So we have seen in many of the cases the when the peak warns out, then a steel to steel or metal to metal contact gives us a sudden failure actually. But if we can capture a method for detecting the wear in the pistons, that would be nice. So we can model this wear by reducing the thickness of the peak and then see what would be the effect. So again, like if there is only one piston, then we have observed in the past, like it has a kind of a different shock compared to the other 8 pistons because you have the clearance a bit more higher, so it has a extra like double shocks we have seen.
I mean, you can have some kind of warning like before you
Yeah,
have the failure. Okay.
Yes, we could have, but as I said, that is, I mean, yeah, it's not like a common for all the pointers.
Yeah. No, it's just like that I was wondering.
Yes.
I told you.
Yeah.
before, you just have like you know, this breaking, it doesn't help too much.
No.
You know, it's broken already.
Yes, I mean, okay, so we have also done, I think it's not part of the presentation here, but what we have done is we also have a lab in Denmark actually, where we also do a monitoring of that in the lab. And what we do there is we put a very close threshold limits. Like, I mean, where we have more false alarms than false negatives, basically. So in the customer, we couldn't do that, but in this case, we could able to do that, and we stopped some of the pumps actually, and before failure. So we could see like one of the rings were open, and some of the failures where one of the springs were broken and things like that. So we have a kind of a database that is we are collecting with different failure modes also. So that is possible.
Thank you.
Okay.
Any more questions? If not, we can thank Vijay again. Thank you for your presentation.
Thank you.